Imagine a phenomenon where sound waves, pure acoustic energy, can produce actual light. It sounds like something from a fantasy novel, yet it is a captivating reality that scientists study. Sonoluminescence, a truly astonishing scientific process, creates light from sound by causing tiny bubbles in a liquid to collapse with extreme violence under the influence of intense sound waves. When these microscopic bubbles implode, they emit brief, brilliant flashes of light, directly converting acoustic energy into light energy. The core mechanism behind this incredible transformation is known as acoustic cavitation. As high-intensity sound waves travel through a liquid, they create alternating zones of high and low pressure. In the low-pressure phases, microscopic gas bubbles form and quickly expand. When the sound wave then transitions to its high-pressure phase, it compresses these expanded bubbles with astonishing force and speed. This rapid compression is an adiabatic process, meaning it occurs so quickly that there is no time for heat to escape the bubble. This traps and intensely heats the gas inside the bubble to incredibly high temperatures, often reaching thousands of degrees Kelvin. At such extreme temperatures and pressures, the gas within the bubble ionizes, forming a tiny plasma that then emits the light we observe. Scientists typically achieve sonoluminescence in laboratories using a device called a sonoluminescing flask. This flask contains a liquid, frequently water, and is vibrated by specialized components known as piezoelectric transducers. These transducers generate precisely tuned, high-frequency sound waves that converge at a specific point within the liquid. A single, small gas bubble is then carefully introduced and acoustically trapped at this focal point, allowing it to repeatedly expand and collapse, emitting light with each implosion. This controlled environment enables researchers to study the precise conditions necessary for light production. The temperatures inside these collapsing bubbles are so extreme that they are comparable to the surface of the sun, and the pressures are immense. What remains a fascinating mystery for scientists is the exact mechanism by which this extreme energy is channeled into light, with theories ranging from shockwave-induced plasma to quantum vacuum fluctuations. Understanding these powerful microimplosions could potentially lead to new insights into extreme states of matter or even new energy sources. Ultimately, sonoluminescence beautifully illustrates how energy can be dramatically transformed under specific conditions. It showcases that the seemingly gentle medium of sound, when concentrated in just the right way, possesses enough power to create conditions as extreme as those found in stars, literally coaxing light from darkness within a tiny collapsing bubble.